Let's see. My name is Jason Biggs. I work as a developer for Wolfram Language chemistry content. And in the past few months, I've been preparing some Paclets. And so we're going to talk about those. All right. Yeah, so the outline slide. First, I'll just go briefly over like what you can do with chemistry in the Wolfram language. A little bit about the Paclet Repository, which is new, which is a feature that has been long sought after, and I think it's well worth the wait. And then we'll go through 4 different Paclets that I've got prepared, 3 of which have been published. One is soon to be, and then I'll say thank you to the people who help. Okay, so I always like to start with a brief overview of Wolfram language chemistry, right? So initially, back in version 6, we introduced the data Paclets. We have chemical data, element data, isotope data. These are things that have curated data, right? So this data has been, there were experts who gathered the data and put it in a compiled form. So you've got something like isotope data, where we periodically go through and find the published list of all the isotopes. We update the mass values, their decay rates, and then we make these things available to you in a function that's very easy to use. So you've got isotopes and you've got properties. And so that's been around for a long time. Then starting in version 10, we kind of expanded the number of domains on which we have data for, right? So you can just do entity value open close and it returns all of the types of entities that we have, right? So we have not only chemical, isotope, and element, we also have cat breeds and famous math problems and food alcohol labels, right? So it's a big expanding ecosystem of knowledge, right? And with that, you can look at all of the different properties that we make available for different things. So for chemicals, we have all of these types of properties. And these are things that need to, again, require a curation, right? They have to exist in a database. There's a limited number of entities available, and we have all of these properties for it. But then starting in version 12, we introduced these new data structures that allow you to represent any type of entity, any type of chemical entity that's not in any database, right? So with an element entity, you've got a carbon. It represents all of carbon, but you can represent a specific atom of carbon with with a plus charge on it, and with 3 different with 3 different bonds. So it's one particular atom, one particular bond. You can represent a molecule. And so this was the big step forward, right? An arbitrary chemical structure, not one that was in our knowledge base, not one that's in PubChem. You can just sit and you can draw it, or you can write it out in a smile string and you can represent it. And so from there, we went to molecule pattern, biosequence. So you can represent, let's say you just have the sequence, this long sequence of letters, and you know what type it is. So you can just have that sit in your notebook. It'll have a set of properties. You can do computations with it. And then we move to having chemical reactions. We have a pattern reaction, which is a templated type of reaction that looks for patterns on the left-hand side and transforms them into the patterns on the right-hand side. You can also represent just a chemical formula. Sometimes that's all you have. And so you know it's a particular formula, so you can compute its molecular mass, you can compute, you can put it inside a chemical reaction. And then more recently, we introduced chemical instance. So you can represent 5 grams of HCl or 2 moles of nitrogen at 77 Kelvin. And so I always like to kind of go through this. So you can take the most simple biosequence that you can imagine, right? And you evaluate it, you get this biosequence, then you can convert that into a molecule. This particular molecule is pretty easy to find in our knowledge base. You can have it as a chemical formula. And then finally, you can ask, does this biosequence match that formula? And we provide the function for that. So these are all different levels of coarse grainness for looking at the same object, the different lenses. Yeah. Yeah. Let's see. So we have a pretty good idea of how it should look, right? So we could call PubChem, we could call some other, so we could look at the knowledge base and say, what kind of coordinates do you have from it? Do we have a crystal structure for it? But we can also pretty much just from scratch generate 3D coordinates. And right, so I mean, in general, these things are rotatable bonds, right? We like to call them floppy. Like when a molecule has a lot of rotatable bonds, we say it's a floppy molecule. And so this structure right here, it's going to have a set of bond angles and bond torsion angles and bond lengths, and all of those are in general averages. And when the larger the molecule gets, the less you actually can be certain that it spends all of its time looking like that. But with a smaller molecule like this, it's fairly reasonable. But this bond right here, right, is very rotatable, and so that guy, it's the let's see, the barrier to rotation, the energy barrier to rotation around that bond is probably really low.
Okay.
Yeah.
Are they inside of that molecule object or computed on the fly?
They can be both, right? So you can create a molecule, like you import a mol file or an SD file or an XYZ file, then they live in the molecule. But if they're not there, then they're computed as soon as you ask for them. And you can also turn that off. You can say set options molecule atom coordinates goes to none, in which case we will never compute them automatically, and you just always have to compute them. Because some people do find it disturbing when we just create coordinates out of thin air. And so that's for them. Okay, so I want to talk now the Wolfram Paclet Repository, something I've kind of been excited about. Before I joined the company 5 years ago, I was a part of the community. So yeah, I mean, this is something pretty big. Okay, so there are internal and external submissions. It's really nice to work with because there's very fast turnaround. Like I notice a bug on there, I can just submit it, and it's live within minutes, really. I mean, it's gotten to be really good like that. And the notebook interface for submitting it is actually very nice to work with. Let's see. So we in the chemistry team, we're using a particular publisher ID, Wolfram Chemistry. I'm going to go ahead and click this. Yes. Right. So it takes you to the Paclet, to the resource system, and it shows you the 3 different Paclets that we have submitted in our group. All right, now I'll go back. So what are we using the Paclet repository for? What I really like is the fast prototyping. Like I said, you can put these things together, you can submit them, and people can be using them like right away. Niche functionality. One of the Paclets I'm going to describe here is, I think, not the most interesting for, let's see, not so broad of an audience, right? And so, but you can just package this up and put it out there, and it's really easy to use. And another thing that's great is making little wrappers for external frameworks. So to say there's some really nice Python package that you want to use, and you don't actually want to do anything in a Jupyter notebook. Well, it's very easy to write Wolfram language functions to call it. And yeah, so that's the basis for one of these Paclets that I have here also. And then finally, one more that I intend to work more on is adding like a documented interface to some of these super functions that we have in Wolfram language, like feature extract. We have molecule value, which when you create a molecule, there are hundreds of properties that you can ask for. And that can be hard to find in a documentation page because you have to search through that entire doc page, and there's not going to be options for every one of those. So those are the kinds of things that can go into a Paclet and have options for. So I want to point out there on Thursday and Friday, there are quite a few talks regarding the Paclet repository. Okay, so the first one I'll talk about is molecule fingerprints. So there's a nice Paclet install command. You read in the package, right? And then once you do that, you've got all these nice symbols that are exported by the package. They've all got nice documentation page that looks just like the built-in documentation, right? So it looks just like the built-in documentation. You can make really nice examples here. So you might wonder, what is a molecule fingerprints, right? So it's a numeric representation of the features in a molecule. You convert it to a bunch of ones and zeros, and that allows you to do fast and meaningful similarity comparisons between different molecules. Right. So let's see. So with a molecule fingerprints, right? So let's say we have two molecules right here, and we can say that they have some similarities and some differences, and we could describe, you know, the presence of six-membered rings, the presence of carbonyl bonds. But how could we quantify that, right? So one way would be to look at what are the features that they have in common, right? So within the Paclet, there's an asset of a bunch of fingerprint substructure keys, right? So these are molecule patterns with labels, right? So you read those in there, and then you can create you can look and see which of those substructures are in each molecule, and then you can compare them, right? So we have these two molecules. They both have an aldehyde or a ketone. Only one of them has a dialkyl ether. One of them has an alkyl aryl ether, right? And so you can take those and get their fingerprints. And in this case, the fingerprints look like an association, meaning this pattern occurs 3 times in that molecule, and this pattern occurs 13 times in that molecule. And then you can take their Jacquard dissimilarity between the two. Or you can just call the function molecule distance, which is from the molecule fingerprints Paclet. And it will automatically grab the fingerprints and then do the comparison between them. Then, so that's the most simple type of a molecule fingerprint, right? That you could, what do you call it? That you have predefined sets of substructures. But a lot of molecules fingerprints use hash-based fingerprints, where the substructures are generated on the fly. It looks at the molecule and it picks out different, it's got a carbon atom here and a carbon atom here and 10 bonds in between them. And that's a substructure. Hash that to a number, and then store all of those. And so you can end up with a huge list of substructures in this way. And then you can, the type of fingerprint that you use can have a big difference on the comparison. So here we have those same two molecules, but we use different fingerprints and different distance functions. And you can find that some methods find them to be much more similar or much more distant than other methods. So this is one of those types of fingerprints called atom pairs, where you have, you search through the molecule and you find all instances of 2 atoms separated by a certain distance. And then each of those is your substructure, and you hash it. And then you come and you get the fingerprint back as a list of ones and zeros. Right. And again, another type is the extended connectivity, where you start with an atom and you look at a circular radius around it, and you include all the atoms within that circle for up to a given radius. And this, I think, is a neat example here. Right, so you can put this into feature space plot, and you can take the extended connectivity fingerprint of every molecule, and then, let's see. Yes, so the tooltips are working. And so I always think this comes out pretty nicely. You can really see that it's fairly good at picking out similarities. You can see this group has a lot of fluorination, right? So you mean like this up here, right? Yeah. So you loop over basically every atom in the molecule, and then you loop around, and it can be fairly efficient because it's all compiled. Right. Yeah, and you can. It's common to store these things in databases so that you look up similar compounds.
Or larger molecules like
right. So probably, yeah. I don't really know. Like proteins, right? So they're normally made for small molecules. I think you would want to come up with a different method for proteins. Okay, so just right. So the next Paclet I want to talk about is isomer generation. right? So here you start from a given chemical formula, and then you generate all possible molecular structures with that formula, right? So you know that carbon should have 4 bonds, or a valence of 4, oxygen should have a valence of 2. And so it'll go through and find all of the non-isomorphic graphs that meet those valence requirements. And so quickly, I'm gonna hit bold here, right? Quickly create millions of isomers and read them in as smiles or molecules. And then there's options for customizing it by filtering out substructures that you might not see in real life, right? So a small ring with a triple bond, that's something that is allowed by valence, but by 3D geometry, it's not going to work at all. And so there are options to filter based on that. So let's see, it works pretty fast, right? So let's say we've got C4H8Cl2. You can find all the isomers of that pretty quickly, right? So this molecule doesn't have that many isomers because there's no double bonds here. There's no degrees of unsaturation. Now, find isomers is a system function, which would introduce in version 13, I think. And that makes a lookup call. It calls pubchem, right? So right now I can call pubchem and find that they have 4,000 isomers of this particular entity. But I can use the count isomers function exported by this Paclet, and in just under 17 seconds, it will tell me that there are actually 75 million isomers of that molecule, right? And just to have an idea of what the formula is. So this is C14H24O. And we could generate 75 million of them if we wanted. Or if we wanted to forbid the substructures that I was talking about, then we would be down to 56 million, right? And so the way so there's a function here called list isomers, which we showed before, which will just return them all. But when you're generating 56 million, then you want some kind of out of core way to do it. You don't necessarily want to have all of those in memory. So we have the function generate isomers, which returns an isomers object, right? Which talks about the file size. When I did this, it was running, but shortly thereafter it finished. And so there's a 1.5 gigabyte file on my hard drive that contains all of those isomers listed as a smile string. And so then there's this function isomers has uploads or up values on part and select and map and lots of things, so that you can just read those in and lazily compute over the list, right? So you'll never have to have all 56 million molecules in active RAM at the same time. Let's see. I think I am over at 55 rather than at the hour. So, right. So briefly here, SELFIES is another Paclet that is live and on the server. And so this is one of the ones that is using a Python package. There's a Python package called SELFIES, and this will call pip install on your machine. You need to have Python working, but after that, you don't have to use Python again because it just works in your notebook. So the point about SELFIES is this. So if you have a smile string that represents a molecule, right? This says there's an oxygen, a carbon, a hydrogen, and then there's lots of keys in here to represent rings, and branches are represented by parentheses. What you cannot do with a smile string is split it into tokens and randomly rearrange them and put them back together to get new molecules. If you do, then you'll only end up with single bonds. You'll never get any rings, and you just won't make anything interesting. So what SELFIES allows you to do, you can take that same smile string and convert it into SELFIES where every token is self-contained. There's no open parentheses or closed parentheses. So what that then allows you to do is to reshuffle them and put them back together, and you can always end up with a valid molecule. And so using that, I can very quickly generate 10,000 random shufflings of that, and then using the molecule distance from the fingerprint Paclet, figure out the 3 that were the most similar to the input molecule. And again, it works very quickly. And then these 3 molecules that it came back are nowhere to be found on PubChem. So they're never seen before. Probably not all that interesting in and of themselves, but nobody knows that for sure. This is a Paclet that's going to go live within the next couple of weeks, exposing some of the internal functions that we use for minimizing coordinates for molecules using force fields. But I think we're at 1:55 now, so I will thank the rest of the Wolfram chemistry team and say that people should stick around for the next 2 talks.